Good morning. So we're continuing our discussion of Chapter 4, which is sort of basic physical organic chemistry. It's some of the concepts that one learns in a beginning physical organic chemistry course about how reactions occur. And so we're trying to look at effects on rates of reactions, effects on bond making and bond breaking, and we're seeing various factors. Today what I want to talk about is kinetics and just talk about some basic first and second order kinetics. And I think I'll pick up with the same idea of that reaction I talked about last time. So we talked about last time a reaction. I said, I don't know if it's Sn2 or Sn1 at a secondary center. So today I want to give two examples and sort of walk through the integrated rate equations, first of which will be definitely Sn1, so definitely unimolecular kinetics. And the second will be definitely Sn2, definitely bimolecular kinetics. And we'll talk about factors relating the rate of product formation to concentrations and rate constants. So let's take a similar sort of electrophile to what we looked at last time, except I'll make it a tertiary alkyl halide, a tertiary benzylic alkyl halide. Remember, when you have a halide next to a benzene ring, right, pH is a benzene ring, you get a lot of resonance stabilization of a carbocation. If you have a nucleophile like benzene thiolate, which is a really good nucleophile, that nucleophile isn't going to be able to do an Sn2 reaction. Tertiary centers are too sterically hindered. But if you ionize to form a carbocation, then you can do an Sn1 reaction. So if I took this tertiary benzylic alkyl halide and benzene thiolate, and I mixed them in ethanol, maybe warmed the reaction mixture up a little bit, we would get a nucleophilic displacement of the chloride, and that would occur by an Sn1 mechanism. Just to put that into perspective, that means in the first step, in the rate determining step, we form a carbocation. And so I'll write that out explicitly. Here's our alkyl halide. It spontaneously ionizes in the rate determining step. It spontaneously ionizes to the tertiary carbocation. If I want to write a balanced equation, I can write chloride. And then in a second step, a fast step, the carbocation combines with the nucleophile. And I'll write that this step is fast. And now we form our product. Yeah?
So it just forms the carbocation just spontaneously?
Spontaneously. So yeah, very good question. So you break the bond heterolytically, meaning the electrons go to the chloride. And as a result, now you get a carbocation and an anion. This would occur in conditions that help stabilize the transition state. So remember last time we talked about a reaction-free energy diagram for this type of reaction. We said, okay, we go through some intermediate. We have our rate determining step. We go to our products, right? So this is our reactants. This is our products. This is our carbocation. Technically, it's more than the carbocation. It's the carbocation, the chloride, and the thiolate all in here. But we usually just focus on the high energy of the carbocation. So you're forming that. any conditions that stabilize the carbocation, or more specifically when it comes down to it, stabilize the transition state. And the transition state is a state in which we have partially broken the bond to the between the carbon and the chlorine. That's over here. Anything that lowers that energy barrier makes the reaction go faster. So we're running this reaction in a polar solvent, a solvent with a high dielectric constant. That solvent goes ahead and it favors the formation of the carbocation. Sometimes one carries out this reaction. Usually, this is called a solvolysis reaction. Well, technically, if it were ethanol trapping, it would be a solvolysis reaction. This is typically carried out with some heating. So this reaction probably would go slowly at room temperature, but heat favors first of all, provides energy into the system. Second of all, entropy becomes more important. We're developing entropy as we go from one molecule to two, and so that also favored by heat. So typically for a reaction like this, it might go slowly at room temperature, but maybe at, say 60 degrees Celsius or 70 degrees Celsius, or in refluxing ethanol at 78 degrees Celsius, it would proceed more rapidly.
In cases where there's a carbocation rearrangement, I'm assuming there's going to be a third energy hub?
In the case of a so in the case of a carbocation rearrangement, great example. So you would imagine you're already looking ahead at some of the textbook problems. So the first step would be, perfect example, first step would be ionization. Second step would be rearrangement to a carbocation, usually of equal or greater stability. And then third step would be whatever, say, traps the carbocation. So you'll see, I think in the homework problems, an example. As a matter of fact, I know in the homework problems, I've set up an example where there's a 4-membered ring. I think it's 4. No, it's a 5 or 4. And maybe it's a 5-membered ring, which has a little bit of strain in it, that breaks open, and then you get a rearrangement, and you form a 6-membered ring. So yeah, absolutely. So coming to a carbocation rearrangement here, you would have a reaction-free energy diagram that might look like this, where you have your reactants, you go over one hump, you form your carbocation, your first carbocation. Usually the rearrangement barrier is reasonably low. You might form your second carbocation. And then you'll go downhill to some products here.
Would the overall reaction be slower now that you have 3 energy homes?
Ah, beautiful question. Super relevant. So the rate determining step, after the rate determining step, everything's fast. So in other words, if this step, the rate determining step, is the step that has the highest energy barrier. So this is the rate determining step. Everything after that is going to be downhill and faster in rate. So the short answer is no. I mean, yeah, I suppose you could have 2 that were exactly identical in a degenerate rearrangement, but if you have something that's going to a more stable product, then all the subsequent steps are going to be faster. And sort of as part and parcel to what I was talking about last time, okay, benzene thiolate is a much, much better nucleophile than, say, ethanol. But if we carried out this same reaction and omitted the benzene thiolate and just heated this chloride in the presence of ethanol, what would happen would be the carbocation would get trapped by ethanol. So you would see the exact same rate of reaction. In other words, if the reaction, I'm going to give you an example where the reaction has a half-life of 10 minutes. If the reaction with benzene thiolate had a half-life of 10 minutes, and we omit the benzene thiolate, and the reaction still occurs with ethanol to give the ethyl ether, which it will, then that reaction will also have a half-life of 10 minutes. It's just that in this case, the benzene thiolate is so much more efficient as a nucleophile. And so our reaction-free energy diagram with ethanol as a nucleophile would end up looking like this, and I'll draw it in a dotted line, like so, where we have a second hump. It's still lower in energy, but now the second hump, still lower in energy than the first step, but higher in energy than the other step. Does that make sense?
For this case, would you expect a mixture of products because of those potential targets?
Would we expect a mixture of products? In this case, the benzene thiolate is so much more fantastically nucleophilic than the ethanol that the short answer is not a significant amount that you would detect. But if we had a good nucleophile as a competing nucleophile, let's say azide, where azide N3 minus is a good nucleophile, benzene thiolate is a good nucleophile, then you'd be able to see a competition between them. And yet the reaction would still occur at the same overall rate. The example I'll give, as I said, has a half-life of 10 minutes. That would still be at the same overall rate. Now, playing off of some ideas I talked about last time and ideas that we're going to develop further on, imagine for a moment that we put two reactants in here. So now we had benzene thiolate and nitrobenzene thiolate. Now, what would you expect would happen in this circumstance in terms of the product mixture and the rate?
The nucleophile at the right would make the majority of the product.
And the rate? Remember, rate determining step, competition. The rate wouldn't change. Now let's think about this nucleophile. So if we consider nucleophilicity related to basicity, which in turn reflects the acidity of the conjugate anion of the conjugate acid, which is a stronger acid, or maybe I should just keep this in terms of the base, which of these anions is more basic? The left one. And so which is more nucleophilic? Yeah, because basically that nitro is pulling away and stabilizing the negative charge. So we would predict that the reaction would still have a half-life of 10 minutes, and the product that would predominate would be the product with benzene thiolate. And of course, we could test that experimentally, which is fun. We don't get to do that in this class, but you get to do that in the lab. Other questions? These are good questions. All right, so let's go to the first order kinetics. And we're going to look, and what I want to do is write the integrated rate equations. We're going to keep it pretty simple here. We're not going to do anything fancy here. I just want to work through. So, okay, the rate of reaction means the rate of formation of product. I'll come back to the original example we had on the blackboard with respect to time. And the kinetics of this reaction for a first-order reaction where the ionization is the rate-determining step, that's unimolecular kinetics. In other words, the rate is going to be proportional to the concentration of reactant. So we would say K times the concentration of reactant. And so if we want to work this out, okay, what I can do is say, all right, the rate of formation of product, this is just a basic statement of reaction of what a rate is the same except the negative of the rate of the consumption of the reactant, namely the chloride. So I can say, okay, d product dt is equal to negative d reactant dt. The rate of formation of the product is equal to the negative of the consumption of reactant. We're going to develop an integrated rate equation from this. And then I can just go ahead and take the original equation and say that means d product or d reactant, negative d reactant change in concentration of reactant dt with respect to time is equal to the rate constant times the concentration of reactant. And what I want to do is develop an equation that allows us to relate the concentration of reactant or product to the rate constant and the time as the reaction progresses, the integrated rate equation. All right, so just rearranging that equation and applying some basic calculus, we can work this out. So, yeah. Oh. So if we rearrange the equation, we get d reactant over concentration of reactant is equal to negative K dt. So now we have an expression that relates our reactant concentration to time. We can integrate that expression and we get, or we go and we're going to integrate to find at any given time our concentration of reactant as a function of time. We're going to integrate our concentration of reactant from the initial concentration, our starting concentration, say 100, say 0.1 molar, to whatever it is at time t, and that becomes, okay, d, so we're doing the integral of d reactant over concentration of reactant. And that's equal to negative K integral from 0 to time t of dt. And all of that just works out to give us an integrated rate equation of natural log, it's a half-life equation, natural log of concentration of reactant at time t minus natural log of concentration of reactant initial at time 0 is equal to negative K T. And I'll just put a box around this equation, because that is the gist of first-order kinetics, integrated rate equations. First order kinetics. This is stuff you saw in general chemistry. It's the decomposition of a radioactive element. Radiocarbon has, what, a half-life of 12,000 years, I think. I don't remember the exact number for C14. But basically, after 12,000 years, half of the carbon-14 is left. After 24,000 years, a quarter is left, and so on and so forth. And that's the same thing we're seeing here. All right, so what does that mean? That means, if we rearrange the graph, if we rearrange the equation, we can come up with a very simple graph to analyze first-order kinetics and get a rate constant. And we also can come up with a set of predictions about what a first-order reaction should look like. So I rearrange the equation natural log of the reactant as a function of time equals negative kT plus natural log of reactant at time naught. This is just a y equals mx plus b equation, if you think about that. And so if you graph what you would expect here, and we graph the time course of the reaction, in other words, we put time on the x-axis, and we put natural log of concentration of reactant on the y-axis, we would expect, for a graph like this, a straight line graph. In other words, we would start at time 0 with a concentration, that's our concentration at time 0. That's really small and really hard to read. I'm going to go ahead and just put it a little bit bigger. And then we would expect a straight line graph like so, where the slope is equal to negative k. All right, I always think much better in the concrete than in the abstract. And so let me just make up some numbers here. That should be a reasonable estimate. I don't have the rate constant for this reaction, but as I said, it would vary with temperature, whether we do the reaction at 78 degrees or at 60 degrees or at 50 degrees. So let me make up some numbers here. So suppose, and these examples are going to parallel our homework problems, which will reinforce the concept. So problems, I think it's 4.4 and 4.7 are going to reinforce today's concepts. So let's suppose that I run this reaction where I use, let's say, 0.1 molar concentration of our chloride as our initial concentration. And we already said it doesn't really matter how much benzene thiolate we use because it's not going to affect the rate. We want to have enough that it's going to react with all of it. So maybe 0.1 molar and then a little bit more. I'll just say 0.2 molar. That's probably how I would do this in the laboratory if my goal was to measure rates, just so that we didn't have any problems with running out. It turns out benzene thiolate air oxidizes very easily, so we could lose a little bit of it. So let's just say I run it at 0.2 molar for our initial concentration of benzene thiolate. And just for the heck of it, since we're going to talk about how you might do this in lab, one way you might do this in lab is to say use an analysis, an analytical technique that allows you to measure the concentration of chloride. If you're working old school, that could be a silver nitrate titration and gravimetric analysis. If you're working modernly, that could be a chloride-sensitive electrode that you could insert into the reaction mixture and monitor in real time the concentration of chloride. So I'll say, and we measure concentration of chloride as a function of time. And I'm just going to make up a little hypothetical data table here and show how we might analyze this reaction. All right, so let's say I'm going to measure at time, and we'll use minutes for time, and I want to show how this translates into rate constants. So let's say we're going to make measurements at time 0, 10, 20, 30, 40, and 50 minutes. And let's say I measure concentrations of chloride in molar, let's say with a chloride-sensitive electrode. And I'm going to make up some data here that would be realistic for this reaction. So at time 0, you'd expect to have no chloride present. Right? We're doing this at 100, I keep saying millimolar because that's how I usually talk in the lab, but we're doing this at 0.1 molar. Let's say at 10 minutes, I want to keep our math simple here. Let's say at 10 minutes, we have 0.05 molar of chloride. What would we expect we'd have at 20 minutes? 0.075. The reaction is first-order kinetics. I've just shown the half-life here. Of course, if you were doing this reaction in lab, the question would be, is it going through a first-order mechanism, or is it going through a second-order mechanism? You'd want to see whether the reaction behaved according to a first-order rate law. So you would say, do this reaction with 0.1 molar of reactant and 0.2 molar of thiolate. And then you might do the reaction with 0.4 molar of thiolate, see if you get the same rate constant. You might also do the reaction at 0.2 molar of chloride and see if the rate of reaction doubles. So I'm just going to give us one data set. So we'd expect 0.75. And remember, I'm fudging the data here. And at 3 half-lives, we'd expect 0.88. And at 4 half-lives, we'd expect 0.088, 0.094, 0.097. So this is, again, a hypothetical data set that I've just pulled out of thin air that I now want to analyze and get the rate constant. All right, so let's say we're measuring concentration of chloride, but we want to apply to our rate equation the concentration of reactant. So I can go ahead and say, all right, the concentration of reactant, it's forming chloride, so it's going to be 100.1 minus the concentration of chloride. So we would infer, we would calculate, we would expect that our concentration now was equal to 0.100, and then 0.100 minus 0.050 is 0.050, and 0.100 minus 0.075 is 0.025, and then we go 0.012, and we go 0.006, and 0.003. All right. If I'm going to analyze the data on a log plots are great, right? Logarithms mean you go ahead and you go by a uniform factor, right? So if the logarithm in base 10 of 100 is 2, the logarithm in base 10 of 10 is 1, the logarithm in base 10 of 0.1 is -1, and so on. And logarithm of 100 is 1, logarithm of 10 is, right, 1, logarithm of 1 is, 0, and so forth. Okay, so we take our log here, and I just plugged it into my calculator. We're doing this in natural log, although you could work this in log 10, and you'd need to have a conversion factor of 2.3. So, okay, we take our logarithm here, natural log, -2.30, -3.00, -3.69, -4.42, -5.12, and -5.81. And I want to analyze this admittedly fake data and see if we obey first order kinetics, and I want to extract a rate constant from it. So in the homework problems, I think again they may actually give you real data, because you'll see little discrepancies between idealized values, at least in one example. And so you'll have to say, okay, what's the best fit on this? All right, so we're going to plot on our x-axis. We're going to plot time. And we're going to plot that time in minutes. And I want to pay particular attention to units here, because this is going to be important. And organic chemists are very bad about keeping track of units, which means I always have to check myself and pay attention to my units. All right, and on our x-axis, we're going to plot the log of the concentration of our reactant, namely the concentration of the chloride. And I'll put in some tick marks in my graph. Try to space them uniformly to reflect a uniform measurement here: 0, 10, 20, 30, 40, 50. And I'll put in some tick marks here. And let's go -2.3, -3.0, -3.7, -4.4, -5.1, -5.8. And if I'm able to draw my data points well enough, which I probably am not because I haven't drawn perfectly here, our graph would look something like that. And then if I fit a straight line to the data, it's not the most perfect straight line, but my straight line would look something like that. And the slope of that line equals -0.0704. And the slope of our graph is the rate constant. So K is equal to 0.704. And I should say the slope is the negative rate constant. And if we pay attention to our units, it's going to be per minute, minute to the negative 1. Thoughts or questions? All right, so we said that this reaction that as I've drawn it depends only on the concentration. The rate of reaction depends only on the concentration of chloride, its unimolecular kinetics. Let's now go from the tertiary alkyl chloride, we'll go to a primary alkyl halide. I'm going to continue with my use of benzene thiolate. Indeed, that is a nucleophile that one might well use in the laboratory. And I'll use ethyl bromide as an example. So I'm going to write it as ethyl. You should know ethyl. ETBr. So primary alkyl bromide. I'd use ethyl bromide in the lab rather than ethyl chloride because ethyl bromide is a liquid that doesn't have such a low boiling point. I can get a bottle of it. I can do these experiments. Let us imagine that we do this same reaction in ethanol. Our product would be ethyl phenylthioether plus bromide anion. And now I'm quite confident that this would be an Sn2 mechanism. Primary alkyl halide, we're not going to get a carbocation. So our rate in an Sn2 mechanism, it's a bimolecular process. Our rate, our formation of product with respect to time, we would expect a rate equation that's K times the concentration of benzene thiolate times the concentration of ethyl bromide. In other words, just as in the previous example, if I double the concentration of electrophile, I double the rate of reaction. But in an Sn2 reaction, in bimolecular kinetics, if I double the concentration of nucleophile, I will also double the rate of reaction. So this is what we would call second-order kinetics. First order in each component. Your textbook gives a very nice example of curves that you would expect for the time course of a first-order reaction, a second-order reaction, third-order reaction, and how your product builds up over time. One of the very nice ways if you want to, so you can analyze data like that. Let's suppose, for example, I were to mix 0.1 molar benzene thiolate and 0.1 molar ethyl bromide. You can analyze data like that by nonlinear least squares fitting of the data to an integrated rate equation. But a very convenient trick to determine K is to use a large excess of one component, and then you're going to be able to do a straight line log plot. So I'll say an easy way to determine K is to use a large excess of one component That's going to lead to pseudo first order conditions. All right, what do I mean here? Let's take as an example, we'll take our benzene thiolate. So I'll say, suppose we go ahead and we use an initial concentration of benzene thiolate of 0.020 molar. And I use a huge excess of ethyl bromide. So I'll use an initial concentration of ethyl bromide of 0.50 molar. Now, over the course of that reaction, the concentration of our ethyl bromide is barely going to change. By the time the reaction has gone to completion, the concentration of ethyl bromide is only going to be 0.480 molar. In other words, it's only going to have changed by 4%, a couple of percent. That's not a lot of change. So now we can treat this as first order. In other words, we can say that our rate equals negative d concentration of benzene thiolate dt, the consumption of our reactant. That's equal to K times the concentration of ethyl bromide, right? This is our rate equation for bimolecular kinetics. But if we say, all right, let us just treat this as a constant, throughout the reaction. In other words, let's treat it as our initial concentration because it's not really changing very much. If we go ahead and we say that it's not changing very much, and we just now say, imagine rolling our rate constant and concentration of ethyl bromide naught into a single constant, then you get the following integrated pseudo first order rate equation. Log of benzene thiolate at time t is approximately equal to, within a few percent, negative K times concentration ethyl bromide naught times T plus the log of the ethane thiolate concentration at time 0. In other words, we have just grouped these two together, and now we have the same equation that we had for first order kinetics. Thoughts about what we're doing here?
So because you have such a little amount of the
Benzene thiolate, yeah.
benzene thiolate, you could treat it as, I'm a little bit confused about what you're exactly.
So basically, over the course of the reaction, now at 10 minutes, let's assume we had the same rate. At time 0, we have 0.2 molar or the same profile of the reaction. So at time 0, we have 0.2 molar benzene thiolate and 0.5 molar ethyl bromide. At time 10 minutes, let's say the reaction's gone halfway, we have 0.1 molar benzene thiolate and 0.49 molar ethyl bromide, which is within limits of experimental error, basically the same as 0.5. So you're saying ignore that little difference. With that profile that I've just set out, what would you expect for the concentration of benzene thiolate at 20 minutes.
So the half-life of that, so 0.05?
0.05, exactly. So right, so you're saying basically now if we set up our table at time, and again, this is all fake, made up, pulled out of thin air data. At time 0, it's 0.020. At time 20, it's 0.005 and 0.485. And what would you expect at time 30? 0.0025 and 0.4825. And so we've taken a second order process, reduced it to first order. And we could still do exactly the same thing. We could do pseudo first order in 1, check that. So if you're trying to check, if you say, because remember, in the end, we've learned all of this empirically. We understand how reactions occur from experiment. So if you wanted to check this idea, you could say, OK, I'm going to do the same experiment, except I'm going to use, say, 0.01 molar. Does the reaction go half as fast? I could then go ahead and say, all right, now I'm going to double the concentration of ethyl bromide and do it at, say, 1 molar. Does it go twice as fast? Or I'll swap, if it's practical, I'll swap, which is my limiting reagent, and say, OK, I'll use 0.5 molar of benzene thiolate and only 0.02 molar of ethyl bromide. Do we now see the reaction pseudo first order in concentration of ethyl bromide as opposed to concentration of ethane thiolate? And so in the end, if we were to analyze the data set that we would generate from this experiment, we'd be able to extract out our rate constant. So we would have a graph much like this, where now we had our time in minutes, and we had our natural log of benzene thiolate. And now, when we plotted these data, our slope would be negative K times concentration of ethyl bromide naught. In other words, in this particular example, it would be negative K times 0.5. And you will have in your homework, in problems 4.4 and 4.7, you have one example, I think, that's first order kinetics and one example that's second order kinetics with pseudo first order analysis of the data, and you'll be able to figure all of this out. So the last thing I wanted to take a moment to talk about is units and some basic dimensional analysis. So I just want us to be cognizant of our rate constants here. So I'll say units of K. And for a first order reaction, and I just want to work through the dimensional analysis. So this is A with K goes to product, where we have dP, deconcentration product, dt equals K times concentration of our reactant. So our units of product, our units on the left side of the equation become moles, or molar, I should say, per second, or molar per minute, depending on what measurements you're preferring to make. Our concentration of A is in molar, and that means that our rate constant has to be in seconds to the -1 or minutes to the -1. So those are first order rate constants. Those are the units, time to the -1. If we now look at a second order reaction, and we do the same thing, A plus B goes to product with rate constant K, dP, deconcentration product d time, equals K times concentration A times concentration B. Our units on the left side of the equation are still molar per second or molar per minute, depending on how you make your measurements. I suppose it could be molar per hour. Each of your concentrations on the right is going to be molar, which means the units of your second order rate constants are molar to the -1, seconds to the -1, or molar to the -1, minutes to the -1. But the big difference is you have concentration built into your rate constant there. All right, I think this makes for a good stopping point. I will see you on Friday, and we will continue our discussion of factors affecting reactions and their rates.